I'm Pat Matthews, Associate Dean in University College. Welcome to the final talk in our MLA Lecture Series. Before we begin, I would like to take a moment to acknowledge that we are in the traditional homelands of Native people. We pay respect to elders, both past and present, and we thank them for their hospitality. The Masters of Liberal Arts program addresses a broad range of cultural issues from different academic perspectives. Similarly, the MLA Lecture Series addresses a unique theme each year from multiple academic perspectives. This year, our theme is transition. The transitions addressed this month have been born out of crises. Jonathan Lassos talked about the efforts of the Living Earth Collaborative to reverse the loss of diversity of species. Tim Portlock's luminous digital images of urban environments made apparent a crisis of American values. And last week, Stephanie Kirk discussed efforts to make the humanities public and accessible as a way to ward off their potential demise. There's arguably no greater crisis today than climate change. Hence, it's my honor to introduce today's speaker. Sophia Hayes joined WashU in 2001 and is currently Professor of Chemistry. The goal of Professor Hayes' research group is a basic understanding of the structure and properties of different types of inorganic systems. Of particular interest to us today is her research on carbon capture, utilization, and sequestration. Professor Hayes is the author or co-author of about 70 papers and the holder of 2 patents. Her awards include an Alfred P. Sloan Research Fellowship, an NSF Early Career Development Award, and an Alexander von Humboldt Research Fellowship. Her labs have been supported by the Department of Energy and the National Science Foundation. In addition to research, she has also been recognized for her outstanding teaching and mentoring. One of the pleasures of introducing someone is a chance to look through the gems in their CV. If, like me, you have witnessed Middle School Science Olympiad, teams of 26 students dispersed across a college campus, competing in 17 events, many involving complex, fragile, or bulky apparatuses, you might be most impressed to know that in 2012, Professor Hayes was a KIPP Middle School Science Olympiad coach. So I believe she can do anything, including hacking climate change with science and engineering, which is the title of her talk today. Please welcome Sophia Hayes.
Yes, thank you for the kind introduction, Pat, and certainly marshaling the resources to get those KIPP students on board was no small feat. Thank you all for coming on a Saturday, a beautiful day out, and also the day of a big parade down in Soulard in order to come and hear about something a little bit less exuberant. And this is, of course, on topics of climate change. I'd like to talk a little bit or remind maybe all of us why we're here. I'm here talking about research that's deeply of deep interest to me, in part because it's inspired by this person. This is my daughter, Marina, and some of her friends. And in the 1st grade, at 6 years old, they formed a Save the Earth Club. And they did so because they were so concerned about topics in climate change that they wanted to do something to help save the planet. And they admonished me to actually tell people about my research so that you wouldn't all lose hope. Because I would tell her and her friends, hey, there's some good things going on and we need to get the word out, maybe a little bit more. So I just want to say this is my inspiration, because in our transitions that we're looking at, it's between the world as it is today and the world that it is becoming. And in part, I'm showing a picture like this to say what we see in the world is a changing climate, and in part due to anthropogenic effects, man-made causes of this climate change. Here we can see a smoggy skyline. We know that there are floods, fires, loss of glaciers. All of these point to a situation that is dire It feels dire to us and also to the next generation of kids. And so this is how my daughter got to be an activist in this area. So what I show here is maybe a familiar plot to some of you. Along this top, let's call this the y-axis, are parts per million of CO2. And what's along this axis is time. So what you see some oscillations, but ultimately the trend line is that CO2 is increasing year by year with no foreseeable change. There is no decrease. And so this effect of the rising CO2 levels has been connected to rising temperatures, things that cause all sorts of other environmental effects and other factors, things that we would like to address. Another source for these kinds of data are just in The Guardian newspaper, a British publication. This one comes in on my iPhone, and this is just a screenshot. Every week, to build awareness of what's happening, it publishes this list. And ppm is a unit that we scientists use. It's like a concentration. Think of it like a percent, but a very, very small number. And yet, what you can say is 414 ppm is much higher than the pre-industrial base of 280. And some scientists who are better at climate science than I established that 350 parts per million is the safe level. That's what we would aspire to, what we would like to get back to. But we continue to introduce more CO2 into the atmosphere as a consequence of energy generation, as a consequence of driving cars, flying airplanes, and even some natural processes, a combination of all of the above. So even with all of these dire things, the reason I'm here today isn't really to rehash these things that we hear about in the newspaper and that are coming at us from all forms of media, but to say there's actually hope. And there's hope because there are hundreds, thousands of scientists working on this right now to solve these issues. And I'm fortunate enough to be on some teams that address this. But let's talk about a scenario where we've been successful, because CO2 is a somewhat new problem to us. So instead, I'll remind some of you, and I see that enough of you are of my generation or older, that you may remember the days of acid rain in the 1970s. Some of you will recall all the news reports about acidification leading to the browning forests of Europe, pictures like these, and this comes from our own backyard, not Europe's. But also statues, marble statues that would melt, their features melt by the acid rain that was falling on them. So the world saw this, and they got together. Treaties were formed, agreements were made, and what happened is we decided to address the chemical pollutants that were constituents here that led to the acid rain issue. So it turned out that there was a device, a material sitting on the shelf since the 1950s. It was invented by a scientist by the name of Eugene Hodry, a French scientist over in Europe, and it sat there for quite some time. In the 1960s, he engineered it into a device. In the 1970s, it was introduced finally into cars. And in 1975 is when the legislation came that said this was to be part of all cars, all vehicles going forward. But this invention that now we see as a success story took all those years to launch, is one part of this story. But also, it wasn't without controversy. So I'll just say, first of all of us have one of these on our cars today. It's a catalytic converter. And inside the catalytic converter are special materials. These are the materials that Hodry started to develop, and it was used and developed and refined by others and continues to be refined to this day. But when I say it wasn't without controversy, stories that came out at the time that it was being rolled out into the marketplace were very dire. The dumbest thing that ever happened to the automobile was in the New York Times from the vice president of Chrysler. This is another quote that I'm just taking an excerpt out of it. Worries about added costs, cannot see how this approach will work. It's complicated. It'll be useless within a year. And this is about the device that all of us have on our cars today. So clearly, it was believed to be too expensive, too useless, too difficult to use, and there's no way it could be deployed across millions and millions of vehicles. And yet we have it today, And the effects of acid rain, those are these pollutants called NOx and SOx for short. What you see is also a trend line. This is time along this axis. And along this axis, the vertical one, is how much there is, this parts per million or concentration. So what you can't argue against is the fact that these have decreased over time, of course. So we've removed these pollutants because we saw this problem with acid rain, and we decided to get together to deploy these materials against the objections that were heard at first. Okay, so onward and upward. So what about CO2? It turns out there are new materials for capture of it as well. And I just want to first say, when I say there's hope, that there are hundreds and thousands of scientists working on this, these are just the ones here at Washington University, along this column on the right, that are working along these lines. This is one set of folks working on very different aspects of CO2 capture and sequestration. One team at one university in one country. Imagine that this is spread out over pretty much all universities these days. In addition, I'm just going to highlight the fact that these are my collaborators, and I asterisk two of them because they have contributed a number of slides to this presentation that I'm going to give. And this is work that's largely funded by what's called an Energy Frontier Research Center, but also was funded by the National Energy Technology Lab in a set of 2 different projects. And today I'm going to talk about the top one of those 2. So again, back to this idea of CO2. CO2 is rising and rising with no foreseeable change, so we need to do something about that to stall it, perhaps. And thinking again about new materials, is there a new material that could be used, for example, in a similar way to what was found in the catalytic converter, to filter those components out of the atmosphere or to filter it out of chimneys and smokestacks? So let me introduce this material to give you an idea about it. In the amount of powder of these newly developed carbon sponges, CO2 sponges, the amount that would fill a thimble has the same surface area, as 3 football fields. So a football field is a nice unit of measure for us because it's something we can relate to. It has that much surface area shrunken down into the surface area of that powder that's found in that thimble. And I'll just give that number for those of you who want to know what it is. And we tend to use metric, so 5,300 square meters. We won't do it in yards. So why does it have such high surface area? It turns out it's a designer material. Chemists discovered that they can make these high surface area things by allowing bonding together of different molecules. And there's what I will call near infinite flexibility and tunability because you have the whole periodic table. Actually, we're not teaching in a chemistry room, so I don't have one to refer to. Normally, I have one behind me somewhere. But you have the whole range of the periodic table to play with, as well as some different elements. And I'll talk a little bit more about just 1 or 2 of these classes of materials. But the reason that these have that high surface area is because notice what you have: pores and tortuous paths that go through, and the gas molecules can transit through these and interact and bind either lightly or strongly with these hosts. This is what makes it good as a sorbent, to take that CO2 out of the air. You can already relate to similar materials to these. That one's a designer material, but you already have things that you can relate to in everyday life. Activated carbon is actually a high surface area material, and many of you know of this if you have a Brita water filter or in different areas of your house. Sometimes it's used to remove scents or different kinds of components, chemicals in water systems. That has a surface area of about half of a football field at maximum. Another one is zeolites. Zeolites are one of these kind of designer materials that chemists make and now engineers. We make it in tank car quantities, not just in the lab, and it's used in laundry detergent. It removes some of the oils and scents that come from we people and cleans up our laundry. Also a high surface area material. And then the last one is a newly emerging class called metal organic frameworks. That's the picture I showed you just a moment ago. And these are highly tailorable, and you'll see that they have very, very high surface areas. All 3 of these actually do interact in various ways with CO2 and with other pollutants. They're all candidates that can be used in some form or fashion for CO2 capture. And again, this motif of having these pores and channels and high surface area, in these cartoon versions of these structures, this is what makes them excellent at these sorbent properties, is having that type of structure, that type of form. So chemists then can design materials that interact specifically with these molecules that we want to take out of the air. Back in the 1970s, it was nitrogen oxides and sulfur oxides, and there were special metals that were embedded into materials in order to affect that. Now we're just switching to a different kind of molecule, and carbon dioxide. So how do MOFs work? Let me just show it to you schematically, just to get an overview. There are metal centers. You can think of them as little cubes, and organic linkers. Sometimes this is referred to by scientists, not just not just general public, as being like tinker toys, for those of you who remember that toy. You have these linkers that can have different types, different lengths, different shapes, and different substituents on them, different chemical decorations, if you will. And the metal centers themselves are metals, usually mixed a little bit with oxygen, and again, you have a wide range of the periodic table to sample, so many, many elements. So when you do combos of those, you end up forming these kinds of superstructures, almost like an erector set. And then the way that we chemists would draw that erector set is shown here. The metal centers are these little triangular kinds of units, and in between, we get the amazing and powerful flexibility that's imparted by our friends, the organic chemists. One or two are here in the audience, actually. And the organic chemists have this amazing facility to decorate molecules with atoms that they want. The different colors, black is carbon, white is something else, and red is something else still. In this case, oxygen for red, hydrogens are in white. But imagine that you can decorate these with other types of species, nitrogen, fluorine, all sorts of other things. We get the full flexibility of organic chemistry, which is used heavily in pharmaceutical development, heavily used in the oil and gas industry, plastics and so forth. We get that flexibility combined with the variability introduced by metals. And then together, these are highly tailored materials that can do these kinds of new things that we want to achieve. And so the idea here is that you have this high surface area substance, and this is a schematic of how CO2, this small gas molecule, interacts at each of these sites within these channels. This is the material of the future. So let's take a step back for a moment. That's just kind of giving you a schematic overview to sort of see what the types of materials are and what the vision is. And now let's go into a few specifics. So these, as a general class, are called negative emission technologies, NETs. And let's just think of that NET and CO2 removal in the same breath. There are two ways to get to these negative emission technologies. On this side of the coin is to say, let's reduce the amount of CO2 we produce. This is often the alternative energy strategies, and there's so many good ones. Nuclear power, wind power, solar power, reducing use through incandescent bulbs. There's a number of ways to do this. This is certainly part of the portfolio that will be part of the solution. On this side are a whole bunch of ways of enhancing what are called carbon sinks. And when you are taking CO2 out of the air with one of these sponges for CO2, if you will, that's one of the sinks. So a lot of the research at WashU focuses on these bottom three especially, called direct air capture. This is the one I'm going to focus on today because it's sort of the most out there idea. Carbon mineralization is actually something that's been researched for the better part of 20 years and is also actively researched here. And then geologic sequestration are proposals for taking CO2 underground. These bottom two are two additional talks, so I'm going to focus on direct air capture. Let me show this to you in a different light. So one of the ways of thinking about this is, again, a very complicated graph, and this is out, and I'm sorry I didn't reference it. Let me show it here. There's a National Academies report. I'll give these references at the end, but this is a very recent report that summarizes a number of the things that I'm talking about today. So these figures are borrowed from it, and also it will be useful in case there's something I don't explain fully to your satisfaction. It'll be in there. Okay, also from the National Academies report is this great graphic, but there's a lot going on, so let's talk through it. Along this axis is basically gigatons of CO2 per year. So a gigaton is a very large unit of measure, and these are metric tons. And along this axis is time. So we're looking at the time evolution of what's predicted in the future. Here we are in roughly 2020, and we're looking at that upwards trend of CO2. This is it's a version of that wiggly graphic that I showed moments ago that was increasing without any foreseeable change. There are a number of assumptions in this kind of graph, mostly that are based on economic models, coupled to models of emissions and so forth. So I can't defend everything in it. What I want to do, though, is speak about these strategies and a portfolio approach. So there are three areas that we can think about. There are carbon removal technologies that will bring that trend line and bring it down. There's energy efficiency in this green box that says as we introduce more energy efficient technologies for energy generation, CO2 will peak eventually with our business as usual model, but it will eventually turn down. And then there's this idea of what can we do about emitting technologies to dampen them. So in this graphic, it's meant to say that all three of these can have different effects. This one looks like it has a very big effect, right? It has a large possibility for action here. And so, yet these portions are what bring the trend line, the red one, down to levels that we would like to achieve societally, okay? So keeping this idea in mind of having different scenarios, different strategies. So here is one of the ways of looking at that portfolio of sinks for CO2, ways that we can address it. There was one just last week rolled out heavily in the news about reforestation, using trees as a CO2 sink, and it's an excellent idea, absolutely. So let me say that there's soil carbon uptake, there's forestation as possible, there's this idea of biomass energy, carbon capture and storage, a slightly related topic. And these tend to be low cost and scalable. And again, you can estimate what the impact will be. Again, on the order of 10 gigatons per year is what the maximum estimate is. Looking at the other side of the coin is this idea of what's called coastal blue carbon, this idea that there are places that can be sinks as well along in waterways and the like. And in the middle here are things that we can, as humans, can design and impact. In some sense, nature is helping us here. Nature can help us here, again, with some targeted planting and such. But here is where science can make a bigger impact because we can design materials, find good conditions for geologic formation of CO2, converting it into carbonates. And again, nature is taking care of this weathering of rocks, okay? So in this middle zone, notice that I'm going to make a kind of controversial claim. And it's that direct air capture and carbon mineralization, I put in quotes, unlimited in capacity, and I can explain what I mean by that. Right now, the National Academy and other reports that I'll refer to basically have told us that it's too costly for us to do this, far in excess of $100 per ton, and there are many basic research questions. Certainly these latter two statements are true about it being both costly, and there are still many basic research questions, and yet this sounds remarkably familiar, right? This is what we heard about catalytic converters. And so thinking about this, scalability is important, and again, the ability to design materials can mostly affect this red box more than almost anything else here on this graphic. So this is where we can have enormous impacts. So, messages to take away. So my collaborator, Chris Jones, is a developer of these materials, and I'm a spectroscopist. I study their structure, and I try to give him information to help him develop better materials. So here are some of the key takeaways from the work that we do together. So we need to deploy these negative emissions technologies to prevent warming. And our thesis is that we recognize that there will be alternative energies coming into use, but we will be using fossil energy for decades to come. If nothing else, in the airline sector, so flights and so forth, it's almost certain that there will not be a substitute in the foreseeable future. for airplanes, just as one example. So even if we could go to batteries for cars and so forth, there's at least a few sectors that will still continue to generate CO2. Most scalable negative emissions technologies employ these CO2-absorbing materials for direct air capture, and materials innovations must be combined with process innovations. This is a way of saying we have materials now, they need to be more cost-effective, and can we engineer them to use them more effectively? If we think back to Hodry's example, the materials were discovered in the 1950s, but it took a decade before they were implemented into a device in the 1960s. So they weren't, and then they weren't really deployed widely until the 1970s. So that's sort of this technology adoption window. We're in the materials discovery phase, it's safe to say. And just so there's a little bit of chemistry in this talk, since I am a chemist, I'm going to say one of the schemes that is almost universally used is here's my CO2 molecule. And what almost all air capture uses is some type of nitrogen-bearing group. The exact chemistry doesn't matter necessarily, but what happens is that CO2, in this case, binds and becomes a new chemical. And so this whole process is what we want to optimize. I only want that kind of sitting in the back of your head as we talk through some of the science there. I'm just going to say that this molecule undergoes a little more conversion so that this is the ending point. And that ending point is temporary because it's reversible. We can heat it or do some chemical transformations to cause it to go backwards when we decide we want to squeeze the CO2 out as soon as the sorbent has sucked as much up as it can hold, let's say, okay? So direct air capture relies on these types of what are called amines, amine-bearing groups. We won't do too much chemistry today. All right, so this is the type of thing. So this is gonna just touch on a little bit of science and getting into some details. There is a CO2 uptake curve. That's what this axis is showing, how much CO2 something can uptake, and pressure, and for those of you who are more technically inclined, it's partial pressure of CO2. So what happens is materials are designed so that it has high CO2 absorption capacity and selectivity. You want to grab onto CO2 molecules selectively and let other things pass by. Let nitrogen pass through, hopefully let water pass through, okay? And so here, the ease of regeneration, first you want to take up the molecules very easily, and then you want to hold them tightly until you decide it's time to let them go. That's a characteristic of a good sorbent. And so its ability to be regenerated is important. One of the most common ways of doing that is called a temperature swing adsorption. All that says is I adsorb on this black curve, and so when I get to this maximum sort of level where it's not really absorbing much more, even if I wait for a while longer, then I can swing the temperature, meaning I can heat it up. That causes us to desorb and drop down to this red curve where the capacity is much less. So at cooler temperatures, it absorbs CO2, fills up the filter, if you will, and then you turn a heater on. It releases this CO2 when you decide you want it. That CO2 can be removed, bottled, and maybe turned into another commercial product. That's the whole concept behind most of the direct air capture and even high throughput flue gas capture as well. Okay. So the idea here is you also want materials that are designed to have high stability to humidity and contaminants because that's present in combustion cycles as well. There's another characteristic that just says we want fast absorption kinetics. We don't want to wait a long time for molecules to bind. And then cost is always the bottom line and the bottom bullet here. We want these materials to be cheap and easy to make and easy to use. So we can think about this as two separate sets of characteristics. And just to guide thinking, and not, this is how we materials scientists think about it. We have two different areas of use. Air, it turns out, has a really huge amount of CO2 that we want to capture, a teraton, even a unit that's even gigatons are not so familiar, hard to relate to, but a teraton is certainly hard to relate. Flue gas is basically what's coming out of a chimney. at a power plant, maybe a cement factory. And flue gas is where you have a very high concentration of CO2. It's an easier job to remove it in some sense, just because there's so much of it there. Notice that we have very different distributions or concentrations. So this can be like, so the amount of smoke that's coming out of a smokestack, it'll have about 15%, 10% of CO2 present. But remember, what we were looking at out in the air, that's even the air around us. We're looking at about 400 parts per million, a much smaller number. So you can imagine that the materials would be very different for these two sides of the coin. The working temperatures for things that are going to be out in ambient air collecting that gas is only a modest temperature, whatever we have out today, on the order of 16 degrees Celsius, 61 Fahrenheit. And then if you're in a chimney, though, that tends to be a bit hotter. So a very different set of concerns. And finally, out in the air, for the most part, we have low levels of contaminants, but of course, chimneys have high levels of other things, byproducts of combustion, SOx, NOx, other such. And then finally, there are two different types of processes for those of you who are in the chemical engineering world. There's either, we think of it as extraction versus purification. And so those are two different process types when thinking about materials that are designed for each of those. Okay, so let me show you schematically, just in the cartoon, what happens in these factories and in cars for direct air capture. So you get exhaust for combustion or from combustion or air, and imagine that CO2 is shown in red, but you have nitrogen and other things that are present as well. And what you want is an adsorbent that is selective, of course, for the CO2. It's going to capture and hold on to it. And then eventually you want to be able to remove that. So remove the exhaust once in a while as CO2 is going to get through. It's not perfect. And the idea here is air, with 50% CO2 removed, maybe more. Okay. The targets I hear are on the order of 90% from direct air capture. There's another side of the coin. So this is in the first step. In the second step, you still have this thing with the CO2 stuck into it. We've got to do something about that. And so that's where you heat it, of course, in order to release it. This is essentially a version of that graphic that I showed moments ago. And then you can take the CO2 out for sequestration, conversion into some other product, chemical. And this is the type of machinery, at an actual plant that does this. So there are two sides to this coin, here divided by red. And so here we need especially innovation, for example, on this side where the gas is contacting the solid. Those are those designer solids that I showed you in the very beginning. On the regeneration side, this is a little bit different. In general, it's simply that if we've designed a material well, hopefully it's robust enough to go through many, many such cycles. So remember that these materials are now ready to come back to this side and absorb another slug of CO2 again. And so ideally this goes around and around until this whole material has been, let's say, spent and then has to be disposed of. But ideally this would go through cycles on the order, I hear numbers of 1,000 or 10,000 or more, 10,000 cycles. Okay, so we talked about 1 and 2. Let's talk about number 3. So direct air capture was deemed hopelessly expensive in this APS report in 2011, but recent research and deployments suggest that it can be on the order of $100 a ton for CO2. So this is a chart that shows the capacity for CO2 along this axis, and here's temperature. So this is where costs come heavily into play, because if you think about it, you're at a power plant, let's say, making energy, and you're going to have to spend some of that energy to heat up that bed of CO2 sorbent. And you don't want to do that. That's expensive, of course. And so when thinking about these high temperature materials, here, this is where you have enormous capacity, and these are calcium oxides, but you have to really heat them to get them to release. So that's a tough call. Down here on this side, you have lower capacity and also lower temperature for regeneration. So there's some trade-offs there, it looks like. And so in general, what you see on this side of the graphic are what are called physisorbents. Physisorbents are where CO2 comes in, it touches a site in order to lead to sort of, let's say, a binding that's very weak, and it doesn't chemically convert to something new. And on this side are the chemisorbents. That's more similar to the scheme that I showed you just moments ago, where the carbon dioxide comes in, binds to a nitrogen, and turns into a new chemical. Turns out it's called a carbamate. And so in becoming a new chemical, then to go back in the other direction requires additional heat or other things. The physisorbents, because they're weak binding, it's a very mild regeneration. So the trade-offs of the two say, maybe there's something good somewhere in the middle. And so it's this class of materials, organic and organic hybrids, really where we're working now, actually where the thousands of scientists are working now worldwide, because these look like they have the best solution for us. They have the tailorability so that the material can be made robust and recyclable. And they also have this relatively high capacity. Notice that another class that we've already talked about, zeolites, are here too. So it turns out that zeolites are part of the target for this type of chemistry as well. They have high capacity because they're up here. They're relatively low in regeneration temperature, so it looks like we could design something, maybe along some lines of both of these looking possible. Okay. So I'm just going to tell you only the briefest of results, just to give some insights from things that we've studied. So the team at Georgia Tech has these materials that are largely solids, and this is a schematic of one of those zeolites. And their designer materials have amines, or those nitrogen-bearing things, inserted into the pores of such a zeolite in two ways. One is just to essentially allow long chains that bear those nitrogens come and infiltrate the pores of that solid. And that's called a class 1 material. It has a high density of these. But you can imagine it's almost like you take a sandy substance and you want a kind of oily substance to infiltrate the pores. And there's some difficulty getting it in there. Sometimes the pores get clogged, interestingly. And in my line of work as a spectroscopist, I can see that clogging, interestingly. Another way is to design them from the ground up. It's a bit more expensive, so we can't do this easily at tank car quantities yet, but maybe someday. Those are class 2 materials. These are well defined because they are grown into these shapes, starting with starting materials that instead of shoving those oily chemicals into the pores, they're instead grown with those grafted onto the surface to begin with. This is a slightly more expensive process because it uses more expensive benchtop chemicals, so we haven't done it at large scale. And yet it provides a really useful tool for us because we can study the fundamental properties by understanding the interactions on more idealized things. It also provides a sort of target. If only we could get the commodity chemicals cheaply enough, it's possible that maybe this could be made at larger scales. So, what do we know about that? Well, here's that CO2 molecule, and this is another version of the structure that I showed you moments ago. So it integrates itself, binds to a nitrogen-bearing thing, and so all of these species are things that we can take snapshots of. They all have different fingerprints that we see. And so again, for these different materials, we watch these reactions occur and can provide some insights about how this happens. So back to curves and data. Again, not trying to give you too much to take in at once, but here's CO2 adsorbed, kind of like that idealized curve that we showed just a little bit ago. And here is that pressure of CO2 along this axis. So what you see in black are symbols that go upwards. They start off very low at 0, but they increase very rapidly. They sort of plateau. And the black symbols pertain to one class of those nitrogen-bearing chemicals, a very closely related, almost identical chemical, but with just one substituent change is shown here. The substituent change is just that one vertical line. In the lingo of chemistry, we would say we've decorated it with another carbon. But in doing so, notice that the capacity has shrunken. So instead of getting, let's say, 1 unit, I get, let me pick a better unit. Instead of getting something on the order of 1.25 or so, we get less than half the same amount for that given partial pressure of CO2. And it turns out if I decorate nitrogen with 2 such carbons, 2 such little lines sticking out from it, it's so small in absorption, it's not even on a scale that we can see well. The symbol is vanishingly small and not present on the graph. So what this says is the tailorability, back to this idea of designer chemistry, is that knowing that some of these interact better or react better than others is critical for designing how these might be in future materials. And so obviously these black symboled ones, the primary amines, are the ones to go after. And so that becomes a design element. In addition, using a very related graphic, so here's CO2 adsorbed, here's pressure again, there's something really important. So here, this is that same black symbol, now new colors, so it's that primary amine. But what we've managed to learn about these is that if you increase the density, if you crowd them together, you see that this pink curve has the biggest number next to it, and that number, which is a strange set of units, just says, I've got more of these crowded in a small amount of space. Where they are less dense, in red, is now the lowest curve. So low density, higher and higher and higher density. So all of a sudden it takes off in a very big way. So it points to some unique chemistry that's going on. So what happened? It turns out that the technique that I do was instrumental in figuring this out. And all it says is that when the density is high enough, it requires this picture of having two neighbors close together to affect the reaction to lead to this special product. And so the point about this is that when we design these kinds of materials, we may have just started, for example, with a picture of one nitrogen, because that is part of how the reactivity can go, based on some of the schematics that I showed early on. But because this is a cooperative reaction that requires two such species, it turns out that that can affect strongly how the chemistry occurs. And so this jump in uptake is due to these different interactions between groups. And then knowledge of that lets us design better ones. Okay. So ultimately, all these characteristics are needed in order to have a really good air capture process. And it turns out that each one of these I could check off individually. And it turns out it's really only these, this number 4 to some extent and number 3 that we've addressed by thinking about those nitrogen-bearing groups. So I'm telling you about this in part because materials like these are actually deployed today. So I mentioned Climbworks being at a cost of $600 a ton. So Climbworks is a demonstration project in Switzerland, and they have these units where these are filled with that sponge-like material for carbon that I've already shown you. And a van is shown here just for scale. These are set up on the top of a building in order to just do direct air capture out of what's passing by in the atmosphere in the Swiss Alps. In addition, there's another direct air capture demonstration project out in California in Menlo Park. And this is one where they've talked about very large scale, what's predicted to be 50,000 metric tons per year modules, which is an enormous amount of capture. Global Thermostat is the company that's doing this, and maybe some of you have seen this announcement that ExxonMobil now is getting into the game. And so they've done a joint agreement, I guess, to advance some of these materials in combination with industrial partners. So I just want to say, this air capture evaluation is an update in 2018 of that unfortunate APS report from 2011 that took kind of all the wind out of our sails in the field. But it looks promising, and here they're studying both what's called solution phase and solid sorbents. What I've talked about today are only solids. And they project in this report that costs in the next decade could fall below $100 a ton. So things do look promising after all. But the point is made that low-cost direct air capture is not a sure thing, and it means that new materials, processes are needed, and this marriage of chemists and chemical engineers. So really quickly, is this practical? There's some calculations that do come out of reports like this. So an estimate for negative CO2 emissions is the capacity that needs to be removed is on the order of 10 gigatons per year, which is a very large number. The land area, though, for direct air capture would be something on the order of 152,000 kilometers, which would be like covering the state of Georgia in, in units. Not a good idea to sacrifice Georgia for the sake of this. However, let me just say this. These, of course, would be distributed. A similar analogy has been used for solar energy, and I think the state of Utah was being given up, if I remember correctly. But it gives you an idea of how much land area would be needed. But remember, these are units that actually sort of could stand aside. Almost like a solar farm, you could have a CO2 capture farm. And again, it's still back to this question, why not use natural systems such as trees? There's some numbers here about how what the removal potential is, but also realize that it's a portfolio approach. Direct air capture is completely amenable in non-arable areas where trees don't grow. So let me say a couple last thoughts. So CCS, carbon capture and storage, requires both traditional chemistry and chemical engineering skills. So I know we see so many of our students go off to become doctors, which is a wonderful thing. We need good doctors. But I hope that some of our students can get excited about things like adsorbent design and because of its ability to address these important problems in chemistry. There's all sorts of problems for chemical engineering in all of these aspects about how you design systems that take the material and can recycle and regenerate it are very, very important. And just setting out this kind of Gedanken problem of great ages of science, if you will. Many of us, at least I was at the tail end of the Sputnik era, coming in with the space race. Of course, you might say that microelectronics have captured our attention up through, well, even today, truly. We talk about the information age here, but there's predictions that energy and carbon management is going to be the newest big science enterprise, if you will, for the next couple of decades. And it will be a defining problem of this generation. Let me say a couple of last things. This is the Climbworks Factory. And these are the guys who did it. And they inspired me getting into the field. Just to give you a size scale, there they are standing next to one of the units. So it's kind of, we describe it as maybe like an industrial washing machine size thing. And they're capturing CO2 directly out of the air. But when they're done, they regenerate it and they squeeze it out. And back here in the background, those are greenhouses. They pipe the CO2 over to the greenhouses to be used there. That's one. The other one is they actually send it off to a Coca-Cola bottling plant in the neighborhood of Zurich, and they use it to carbonate soda. So there's direct air capture Coca-Cola out there. Well, so back to the theme. So the transition between the world as it is, and how about not the world that it is becoming, but the world we want it to be? Because we scientists, well, we can engineer and science, to use a phrase out of The Martian, the movie, we can science the heck out of this. And I'm just going to say, so my daughter was the inspiration for this. So she now can hold up that thimble and say, hey, there's 3 football fields full of CO2 in there. Anyway, thank you all for your attention. I'm glad you've given me the chance to talk about this. Yes, thank you.
We have time for questions. And now, as you know, I've been here on one side and try to make myself, if I missed you the first time, I'll try to come back.
Yes.
I heard somewhere, or read, or saw on TV, that even if we stop producing CO2 today, that it takes a very long time for it to break down. And
Yes.
so that we're at these high levels, and it will be centuries before it can come back.
That's correct. The idea, I'd be happy to. So it's the idea that CO2 doesn't break down easily, so we have these high levels that we're facing, and it's not going to degrade, let's say, or go away. Yes, so CO2 is a very unreactive molecule. I know that my talk suggests otherwise. We have to fight hard to make it react and become something else. So really, we're talking about filtering it out. We're generating a lot of it, and so what we only have a couple of choices. Don't generate it, filter it out, or even prevent it from getting out to begin with by, converting it to something else before it gets out into the air. So what I'm talking about today is filtering it out of the air where it's kind of diffuse to solve the high levels that are here today. but there are great strategies for the other parts as well. And there are materials that do it now. It's just costly, unfortunately. Thank you for the question. And I'll repeat it. Yes.
Is the last process that you showed, is that a continuous flow process or a batch process? And also, what energy is used? Because to take the CO2 out of the absorbent takes energy.
Yes.
And what energy is used? What kind of energy is used to do that?
Okay, so the question is the last process I showed a batch process or a continuous process? That's number one. And number two is, where do we get the energy to do this? Okay, so let's talk about the first one. So the first one is, it is generally not continuous flow. It is a batch process because you want to sort of allow everything to suck up and then decide when you want to release it. You want to release it kind of on demand. Most of the technologies that I know about, that's the first one. Where do you get the energy? Well, you've got to get it, you have to use, you're burning coal and you are using some energy, regenerate water.
Is there another question? Because
You get
They just using solar energy, so it's constantly available, as opposed to trying to burn fossil fuels or whatever other energy humans use.
So back to the energy side of the equation, yes, ultimately some energy source is needed to reverse this process because it's just sort of laws of thermodynamics in play there. And so indeed, we have to get it from something. Does it have to be through combustion? It could be through another source. So yes, please.
Testing, it doesn't work. Okay.
That's okay.
What is your impression of climate change, or of man-made climate change deniers?
Impression of climate change, man-made, anthropogenic, man-made climate change deniers. Luckily, I'm a scientist, so I get easier problems to work on than sociology and psychology. Oh, and by the way, the really hard one? Econ. Oh my gosh. Anyway, those guys, tremendous respect for economists. It is hard. All I can say is we just, move forward with the best materials we've got. And we hope that people will come along. So what I admire tremendously is the team that I've been on, even, when things looked pretty dire with these reports coming out, they never gave up. They've been working on direct air capture types of materials for more than a decade, 2 decades even. And the point being that they have, even in lean times of not so much funding or declining interest of the government here in some of these lines of research, they've kept at it. So there's hope.
so this kind of works.
We're not going to.
So my question is kind of an econ question, and you can speak to it. But it's great the cost has come down, but it's never going to be zero. So if you look at the catalytic converter, no car manufacturer wanted to put on catalytic converters, but they were forced to. So is there any thought of, like even this one that's in Switzerland, it's $100 instead of $600? Who's going to pay for that so that all of us have a better planet? Is there any thought of how to go forward and convince industry they need to do this, they must do this, et cetera?
The question is how do we still get the $100 a ton or whatever the price might be? How do we come up with that? Again, an econ question. These are the hard ones. So I'm just going to say, in general, what's thought is that eventually we will have 2 processes. Let me start with the easier one. The first is there's a great podcast about solar energy costs coming down by orders and orders of magnitude, more than 1. And just because of scale. So first of all, when things go up in scale, sometimes that can make it a lot more cost effective. That's the first. But the second one is often, I'm going to say the words carbon tax. is usually what's invoked as a way to pay for that. And yes, the auto manufacturers were forced, indeed. And so right now, I think what we hope is that obviously any tax has effects on our economy, on society, and so forth. And so there has to be a will to do this. And for whatever reason, think back to the acid rain. What was special about that time and place and era? I mean, it was the 1970s. And somehow we all got behind fixing it. There's another really good, tremendous, success story, and that's the elimination of chlorofluorocarbons. Those of you remember that the ozone hole was a big thing. And again, we decided to get behind that. Now, CO2 is a bigger deal and is a bigger problem. But, you see hopeful steps along the way, and I think we're going to get there. I see a couple young people in the audience. They're going to get us there. So, yes, please. These have been so patient.
Where does methane fall into the big picture?
Oh, methane is a terrible one. Yeah, methane's a bad boy. So, but the good news is a lot of these materials that are being developed are tested for methane as well. So it has similar size and so forth, and it's got different properties, but you can bet that we could have a whole separate talk on methane. It's just that's not gaining quite the amount of attention that CO2 is at the moment, because methane is released usually by some other process, sometimes in the oil and gas refining or mining processes. It's not a combustion product, so it's thought of in a different realm, but it is a worse greenhouse gas ultimately. And so yes, people are thinking about it. By the way, zeolites, the ones that I showed a bit ago that are used in laundry detergent, those trap methane already. Now it's reversible, so but there is materials that already do it well. It's just, again, expense. So. Hey, Paula. Uh-huh.
I like to talk a lot.
Thank you.
I'm curious about those oscillations. I don't think it's working. It is picking up. It's picking up? Okay. I'm curious about those oscillations in your graph of CO2.
Oh, yeah.
Are those seasonal?
You're so sweet.
related to plants and
Yeah, I'm so glad you
photosynthesis?
asked. Those CO2. What Paula, because she's a good physical scientist. This is what we do for a living. We look at data and we're like, what is that? I'm going to get there. There it is. Those are seasonal oscillations. This is sitting on top of Mauna Loa, the volcano, and it just goes through a little bit of a fluctuation as you go from month to month. I used to have an inset. I guess I took it out because it was too complicated. But you can see it's not a perfect sine wave. It has a little lag and so forth. And it's way up there above the inversion layer in the atmosphere. So it's considered the cleanest, if you will, CO2 source. But yeah, it's kind of cool, isn't it?
Hello, speaking. Okay. I've read that capturing CO2 that's being produced all the time is not the biggest problem. The problem is producing it. If we can prevent production, that's where the money is. And I know that's political and economical and everything else, but why should we be chasing a problem that is never ending? Why don't we reduce the problem so we don't have to chase it?
Absolutely. So the question is, why don't we switch generating CO2? So let's just take a moment to talk about that. And that's kind of what's shown on this graph. And you see that the green area could have a huge impact if we just, but let's talk person to person. I drive a car. I fly like a bandit. I go all over the country in planes. I feel guilt about this myself because I'm a gasoline user. And I don't think I can switch wholly off of gas to other alternative sources of energy anytime soon. And because of that, I'm a little bit of a realist, saying I should put solar panels on my home, I should do all these other things, and I could to cut my energy use. And we all should be doing that, and to the extent we can. But we first of all have a lot of CO2 in the atmosphere now that needs to be cleaned up. The second thing is, we could switch away from fossil fuels, and that is absolutely a good strategy. But we can't go cold turkey. So for several decades at least, if not longer. We will continue to do this. And because we will continue to use or to generate CO2. And so let's do something as almost like a Band-Aid measure in the meantime. I think all of us would like to see less reliance on fossil fuels, but ultimately, you know, if you could come up with a way to clean that up, it's kind of a win-win for everybody. And it lets us wean ourselves off of oil and gas in a shorter time frame, you know. I hope that's a good enough answer. No? Well, we'll put it this way. I'm very interested in alternate fuels too. No, don't be. It's part of the debate. Here's the thing. We have to do all of the above. That's actually what we should be doing. Yeah, no, I appreciate the question. You can shout it out, I promise.
Yeah, I think I can. My question is kind of related to that, but if you picture this just simply as a smokestack as the source of a lot of CO2, what's the concentration difference inside that smokestack as opposed to the atmosphere? And doesn't it make more sense to do what you're doing, capturing it in the smokestack as it's being released from a power plant?
Yeah, so that's same technology, just a different kind of material. And yeah, so when I showed that table with 2 columns, that's the smokestack. Smokestack is 10-15% CO2, and in the atmosphere, parts per million, you know, much less than 1%. So we're talking about 2 different sides of the coin, 2 slightly different materials. At least. So the issue there is just how, you know, you could, materials that you design for one can, let's say I'm in the lab, I'm accepting different gases. One is good for one type of application, one can be good for the other. Can I give this to him? He's been waiting so patiently. How about if you speak to that? And you can
Well, one thing is a comment, and the other is a question.
All right.
The comment is that I've lived with the idea that heating of this planet is not a hypothesis, it's a fact. I go back 72 years in my simple observations, which require nothing more than a measuring stick. And I am following what the Swiss are doing. The measurement of the recession of glaciers. There is scarcely a Swiss glacier in performance today. They're all gone. Anyway, now the question is this. How about a direct conversion of carbon dioxide to carbon and oxygen?
Okay. So I think you all heard that question. So that's a very hard, require a lot of input energy unless we trick the molecule into doing that. So a complete break, if you will, of CO2 and carbon and oxygen constituents is a very challenging. Boy, I'm fading out too. It's a very challenging problem that requires sort of an uphill driver to get you there. Sometimes we talk about that being something, a special type of chemical, like a catalyst. But hold on a second. When we think of expensive things in terms of energy use, that would be even more costly in terms of energy. So we're trying to do this on the cheap, maybe, and easy. It would be easier and cheaper than breaking it apart. But I appreciate the creative approach because we could come up with alternative strategies if we found a magic catalyst to get us there. So it's good to think out of the box. There were some other questions. This one is National Academy of Sciences, however much fiction they and their scientists put into things. But they're a very esteemed group of people. I would assume they did good homework, but those of you who've ever heard me talk on helium, a completely separate topic, know that I'm kind of down on National Academies. That's on camera. Because they made some mistakes in a policy paper. So no, I can't really defend this. It's only a schematic to say, let's think of more than one thing. Let's look at what has big impacts, and this idea, it's very cartoonish, and I mean, there's thousands of assumptions. I mean, as a scientist, trust me, I'm...
There's going to be a gross negative CO2 emission starting around 2035.
It's the possibility, can that be true? I mean, this is predicting the future, and I think there's a lady with a crystal ball down the street that actually would be able to give you a different version. So of course, this is using some, guesses of what might be aspirational as opposed to, do we have a policy in place? No, so it's aspirational. And again, in the report, it talks about these as possibilities as opposed to, yeah, we have a defined strategy. Just useful to guide thinking and colorful. So, yes.
I'm trying to mentally just multiply out the math on this.
Mm-hmm.
You said $100 per ton, metric ton, I presume. There's 10 gigatons that need to be removed annually?
Yes.
Okay.
Actually, I have the number, but yeah.
Okay. So that's $1 trillion. Is that the math? What's $1 trillion a year? No, $10 trillion.
So 10 gigatons is to get us below, let's see, we're currently producing, I actually wrote it down because I thought I'd get this. It's 36 billion tons per year is what we produce. The 10 gigatons is the idea that you would remove to get us back down to 350 ppm.
So I'm just trying
Yes.
the rough math.
Yeah.
We're clearly talking in trillions of dollars.
Absolutely.
In annual expenditure globally.
So here's the trade-off. What's Miami worth? Is kind of that's how we have to start thinking about it. And we might be able to get rid of Miami. I mean, it's not that great, but it's hard. It's hard to. Yes, I understand where you're coming from, and those are why the econ part are the harder questions. So.
But I think it's also helpful to the message.
Yes.
This is a big problem.
Well, so I have a conflict of interest because I do research in this area, but if more research was funded in this area, because there are so many people working on this, maybe, again, some amazing discoveries have been made, and then you just think, is there something sitting on some shelf somewhere that, we could be using today if we just had, the desire and the will to do it? But, the guys that I work with are brilliant people, and I'm just a spectroscopist. I mean, they are the ones that make this stuff, and they can do magic things that are incredible. And I think what I wish to say about that is they kept the faith, even when things have looked really bad research-wise for a number of years, and they're continuing because they're working on it for our kids, and for the sake of the planet. They're true believers as opposed to, hey, I'm in this to make a buck. And so in that sense, you all should take hope that there are people most scientists are like that. I know some of my science colleagues are here and they are the same way. So we work on these things because we believe it'll make the world better. So yeah, so it's a lot of money. I mean, that's a problem. Yeah, please.
Is anybody working on artificial photosynthesis?
Oh, absolutely, yeah. Artificial photosynthesis is, oh my goodness. I wish I could answer that adequately. I think maybe some of my colleagues who are here could do a better job. Those are also designer molecules, and they have learned great things about how artificial photosynthesis, so in other words, how plants can take in light, or a synthetic plant could take in light and convert that to other chemical forms or electrical forms of energy. Yeah, that's still exciting, but nothing that has translated, to the best of my knowledge, out into the marketplace. Again, I'm not as good of an expert there as I could be, but it's an exciting area because you can use all the processes of biology. Over here, if any of you have a chance, in fact, if Pat's still around, yeah, so you should someday arrange a tour. I don't know if all of them could go, but over at the combustion facility, so there's a combustion pilot plant, a 1 megawatt plant here on campus. They can burn different things like coffee beans or husks or something, I don't know. And then they take the combustion products and they pass it over banks of algae that have been genetically engineered. So again, maybe you know some of this, and those banks of algae have artificial, or real in that case, photosynthesis going on that have been bioengineered to either do something with that sunlight and the presence of these, CO2 capture gases and stuff. So it's a really neat unit. So I'm sorry I can't give you any more of an update, but there are fascinating things going on about that. So, yes, please.
This whole series for this entire month on Saturday mornings has been outstanding. Last week we had a person here who argued about the value of the humanities. I'd like to have her standing here this morning, because when you made the comment, we're going to science the heck out of it, that's fine. There's good reason to believe we need to do that. Nonetheless, the comment here is there must be a value in the humanities. You talked about the 70s. I'm making a quantum leap here in terms of assumption, but maybe it's because the humanities, and we know this in terms of data, was much more prevalent in a university like this. Today, we're going to science the heck out of it. Now, maybe our interest as a population was due to experiences of a combination of science and the humanities. Camus' play, that novel, has certain relevance today. It may even add something to the will that you referenced about those few that you work with that do it for those important reasons. I don't know. But I think that it's a wonderful juxtaposition that this series provided for us, and we shouldn't necessarily dismiss them. A question. What humanities, if any, do you find pertinent to the work that you do? That you get to the point we're going to science the heck out of it. Well, what moved you to that position?
Oh, all of it. You know why? You've picked on the wrong person, I fear. My grandfather was a theologian. My sister is a historian. Another sister is a business-oriented person. We all cared deeply about language. We learned how to write and to speak and articulate early on, and we were never given a chance to escape to, or I was never given a chance to escape to my math and science and calculations without discussing the latest, piece of, literature or something along those lines. So part of why I can talk about this the way that I do is that background and training. I had a very deep set of training in the classics, lots of Greek and Roman literature, not in the original languages as my grandfather did, but at least, in English translation. So no, I'm afraid I'm a huge proponent for the humanities and think that we should do more. I teach science writing. And so part of all of the communication that you see up here, imperfect at best, and I could have changed a few figures, but part of that is all derives from the humanities and not so much from my scientific training, I fear. So I'm with you, man. Is all you can say. So you got the right person. You got the right person for the series. All right. Seems like we're wrapping up.
And that was a great way to
Indeed. On the humanities. Thank you all.